Now, if you think about this, what exactly you're trying to do is you're trying to compute the difference between the pixel intensity with the neighborhood, right? All the pixels like in the neighborhood. Now, if you think about like the amount of computation you require, for each location, you will have that many computation steps. Okay, and if let's say the image resolution is 600 cross 600, the total number of computations you'll have to do to get that response for an input image, it will be almost 5.2 billion operations, which is a lot. Okay, so it will be computationally expensive. And that's why we have like optimized algorithms to do that. And I will just briefly give you the intuition like how we can optimize this without going into more detail. And you don't have to worry about like if you don't understand any part of that. Okay, so before that, if you think about what exactly we were looking for, we were looking for like a strong peak, something like this. Okay, so this peak represents if a current pixel location is actually distinct from the neighborhood. And that's how we define interest points. So if you look at this, the surface, it actually looks like something like this, right? You can kind of approximate this with this bell curve here or bell surface here. Okay, so that's a quadratic surface. And now what we do is we try to approximate that using a different function. And before coming to that, we'll need, I think, Taylor series for that. And again, don't worry if you don't recall Taylor series or anything. You don't have to really understand what's going on. But if you do, I think that's really good. And I will be happy to like discuss if you're more interested in this during the office hours, but I will quickly run through this. Okay, so Taylor series, you can approximate any function using this series. And in the series, you have like different set of derivatives. Okay, so if you compute derivative at any given point, then you can compute like multiple derivatives and use them like to represent this function. For example, the series over here, we are computing derivatives at point A, and that function, the original function f, can be represented by this series over here. Okay, so you have the original function value at A. This is the first order derivative, second order derivative, third order derivative, right? And usually like the higher order derivatives actually will give you very small values. So if you have to approximate, you can actually just get rid of these higher order derivatives and maybe just use first 2 or 3 terms. Now, if you look at this simple animation, the actual function you had was exponent of x, okay, the blue curve. And the red curve is actually showing you, it's trying to approximate this function using Taylor series. And if you look at these values of n, this is like how many terms we are using. Okay, if you just use the first term, you can see it's just like a horizontal line, okay, because it's just fa, right? It's just one value. And if you take 2 terms, then we'll have to compute this first order derivative, and then you have the slope as well. So that's why the horizontal line. And as you keep including like these higher order terms, you can see that nearly, I think, n equals to 5 or 6, you're kind of very close to this function. Okay, just like very simple example here. Now, why that is important? Because now what we want to do is we don't want to compute like this point-wise difference. We want to approximate this. Okay. So how we do that? We actually compute the second moment matrix, and this is using image derivatives. So basically, this equation over here, this can be approximated by the simple matrix multiplication. And again, as I said, we don't have to worry about like how we get that approximation. It's like a long theoretical proof. But this is a way to approximate that equation. And in this one, this moment matrix here, why derivatives are important, why we're talking about derivatives, because this moment matrix is actually composed of derivatives of your input image. Okay, so this is exactly your M matrix. And these symbols are like, this is your first order derivative, partial derivative in x direction. Again, you multiply x and y. This is the same term. And this is partial derivative in y term. All right, so now the idea is once you have this moment matrix, you can actually compute this response. And this response is like all we care about. So what we do, given an image, we just compute these partial derivatives. And we'll try to combine them to get that M matrix, which will give you the final response. And there are a lot of heuristics involved. So it's not that it was invented in a day, week, or month, or year. I think it's like research of several decades. So I don't like expect you to understand this like just in one lecture. And that's why I said, don't worry about, but just try to understand like the overall steps which are being performed like in this algorithm. Okay, so let's say this is your input image. We compute like partial derivatives. This is in X direction, and you know that how to compute this, what this means. This is basically just like edges in X direction, right? Similarly, you can compute edges in Y direction. This is the XY component. And you can just multiply these two. That will give you the second part here. That part is also similar. Okay. And you can also like just multiply IX with itself. That will give you the first term over here. And if you multiply IY with itself, it will give you the fourth term. So using image derivatives, you can get the elements of this matrix.